بسم الله الرحمن الرحيم. اليوم نبدأ معكم محاضرة رقم 14 في Digital Signal Processing. تكلمنا في المحاضرة الماضية عن Discrete Fourier Transform DFT، بس حتى نبدأ في دراسة البروبرتيز تاعونه كان لابد من التوقف شوي وشرح شيء بالنسبة للسيجنالز والعمليات أو البروسيسز that we are doing over signals. هذه العملية اللي راح نشوفها أو هي شيء مهم بالنسبة للدي اف تي، عشان هيك أنا اضطريت إني أوقف شوي في شرح الدي اف تي والبروبرتيز تبعته حتى أشرح هذا الموضوع. الموضوع هو إشي بنسميه إحنا circular shift and circular convolution. circular shift and circular convolution. يعني circular shift يعني مش شيء محبب، لكنه احنا مضطرين نتعامل معه لانه مهم بالنسبه للدي اف تي او للديسكريت فورير ترانسفورم. What is a circular shift? So we'll go with the first item of our headline, اللي هو circular shift. Before we define the circular shift, we need to define the modular operation. The modular operation. So this is a new operation that we would like to discuss with you. The integer r obtained by evaluating m modulo n is called the residue. الباقي نسميه الريزيديو أو الباقي، and is an integer value between 0 and n minus 1. Yeah, and this is something normal for positive numbers, you know. إذا أنا بدي أعمل الانتجر r هو عبارة عن حاصل قسمة m على n والباقي، إحنا بنأخذ ال r هو الباقي، ده الريزيديو، حاصل الناتج من حاصل القسمة. أوكي، لكن بالأرقام السالبة راح نشوف هلا إحنا وياكم كيف تعمل. So the modular operation is defined by the notation r equals m modulo n. أنا بنستعمل البراكتس هدول اللي هم زي الأكبر والأصغر، modulo n to represent that, or to say that you are doing m modulo n. What is m modulo n? It's r equals to m plus some integer values times n, where L is an integer, could be positive or negative. Chosen to make, so it is chosen to make R a number between 0 and n minus 1. Okay, so we have to look for this number. Okay, let's do an example and see how we are doing this. If you are doing, let's say 25, which is m, modulo 7, which is n, then you are looking for this. M is equals to 25 plus some L that I'm gonna look for, plus or times 7 multiplied. So this L is multiplied by 7. Okay, so the answer should be R. R is equal to 25 modulo 7. The answer should be a number between 0 and n minus 1. What is the only L that we can use, positive or negative integer, such that the end result here to be a number between 0 and 6? If we choose this to be minus 3, so if we choose this to be minus 3 times 7, 25, then this is equals to 25 minus 21, and this is equals 4. So R is equal 4. And actually, if you divide 25 divided by 7, then you have a 3. 3 times 7, it's 21. And if you take the difference, it's 4. So you don't take this one. We are going to take the residue. Residue. Okay? We'll take the residue. So the residue is equal 4. So our R is equal to 4. So this is the case for the positive integers. What about the negative integers? Let's take another example. R equals to minus 16 modulo 7. So minus 16 modulo 7 is, again, it's a number, minus 16 plus some L times 7. So what should we take here to make this number value between 0 and 6, and 0 and n minus 1? N is 7, so n minus 1 is 6. And we actually going to take the same number here, but with a positive value. So it's plus 3 times 7, and it's equal minus 16 plus 21, and the answer here is 5. So R in this case is equals to 5. R in this case is equal to 4. So R is equal 5 for the minus 16 modulo 7. For the 25 modulo 7, it's equals to 4. Okay. So this operation actually, or the modular operation, is we're gonna need it to represent to mathematically represent the circular convolution. Okay. So we are using the modular operation we define the circular shift of length and sequence x of n by x sub c of n, circular shift of n, is equal x of n minus n0 modulo n, where x sub c of n is also a length in sequence. If n0 is greater than 0, it is right circular shift. And if n less than 0, it is left circular shift. Okay, left circular shift. Let's represent this by an example and see how we are going to do this and how we represent this by mathematically and graphically. I'm going to take an example. I'm going to have signal starting from 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, and 5. This is my n. 1, 2, 3, 4, 5, and here is 6. So you have this sequence, 6-element sequence, starting from 0 up to n. So this is my x of n. Okay, I'm gonna do x of n minus 1 modulo how much we have, so it's 6. So minus 1, then you are doing right circular shift. X minus 1, you shift it by 1. So what we mean by circular shift here is that the sequence has exactly the same length. So the one that will go, when you shift it to the right, it will go by 1 step to the right. This one will go here and circles and enter the empty space that we are going to have here. So if you want to look at this, so you have this 0, 1, 2, 3, 4, 5. Okay. If you do this, then this one will move and come to this one. So this one will be 6, 1, 2, 3, 4, and 5. So this is our x of n minus 1 modulo 6. X at 0 is 6. X at 1, 2, 3, 4, 5, and so on. And we can do this xc. So this is your xc of n. xc of n is equal to x of n minus 1 modulo 6. So xc of n equals. So if we take xc at 0, so this is x of minus 1 modulo 6. And this is equals to x of, so you're gonna, this is minus negative. If you apply the modulo operation, minus 1. So let's do the modulo operation here. So you have minus 1 modulo 6. This is equals to how much? Minus 1 plus some L times 6. So you will have L equals 1 times 6 minus 1 plus 6, and it's equals to 5. So this one will be x of 5. So x circular shift of 0 is equal to the normal or the input of x of 5, and x of 5 is equals to 6. X circular of 1 is equal to x 0 modulo 6, and this is equal to x of 0, which is equal to 1. Okay. xc of 2, it's equals to x of 2 minus 1, it's 1 modulo 6, and 1 modulo 6 is x of 1 itself, which is equal to 2. And we will continue, and you will get the sequence. So if you continue here, you will get exactly the same sequence as we have here. So the only change that we have from doing the circular shift is this one. Actually, you can look at this one here to be one step in this direction, or you can look at it if you wanna do it. So it's one step circular. This is why we call it circular shift. Everything goes up, out. It doesn't go out, it goes back in a circle and enters once again. And you always have exactly the same length, but with different locations of the samples. Okay, look at this one here. It's x of n minus 1 modulo 6, and this is the answer. If you do the left shift, so if you want to do a left shift, then you will start taking this one here, and this one will goes down. So it goes down. If you goes down 1, 2, 3, yeah. So it will go down 1, 2, 3, 4, 5, and you can say that if you move this one 5 times to the left, it is as the same as moving it one step to the right. So this one is also equals 6. This is also xc of n is also equals x of n plus 5 modulo 6. So 5 steps to the left is equivalent to 1 step to the right. And actually, you can look at this number here, n, and this number here. They are complement of each other. This is 5 plus 1, it's equals to 6. And I am sure that if you take xc n of n, which is equal to x of n, let's say minus 2 modulo 6, this is also equals to x of n plus 4 modulo 6, and so on. So this is always true. Make sure that it is okay, yeah? Okay, one more example. If you have x, we need to find x of n minus 4 modulo 6. N minus 4 modulo 6. So here we have it, we move it once. You have to move this one also, this twice. Then this one 3 times, and this one is the 4th time. So you end up with the last 2. So this is 0, 1, 2, 3, 4, and 5. So you have here 1, here 2, 1, 2, and then you have here 6, 5, 4, and 3. So this here is x of n minus 4. You have 4 samples moved from 1, 2, 3, and 4. They are all moved and entered. The first one enters is 6. So here 6, 5, 4, and 3. And actually, you can think of it as if you are moving this one and this one to the left twice. So if you move this one here and bring it here, one time, this the second time, so you have 1 at the location of 4 and 2 at the location of 5, and this is what we have. So this one is actually equals to x of n plus 2 modulo 6. N plus 2 modulo 6. Okay, so this is what we call the circular shift, and this is how we implement it. We are taking this in a circle, so you don't have any excess when you go to shift left or shift right. You don't go to beyond the indices from 0 up to n minus 1. You're always within this window of indices from 0 to n minus 1. Anything goes out, it goes back on a circle and enters once again, either from the right hand going to the left or from the left going to the right, and so on. Okay, now we are going to use this concept, the circular shift, to implement some new operation on sequences, which is called circular convolution. So we will define the circular convolution based on the circular shift. So based on this type of operation, the circular shift, we are going to define the circular convolution. Okay. So the previous convolution that we had before, we had to rename it and call it the linear convolution. So the linear convolution is defined as before, and it's equal to the summation from k equals 0 up to n minus 1, because we would like to unite our definition based on finite length sequences and n-length sequences, always starting from 0 up to n minus 1. So this is x of k, h of n minus k. Okay, so this one will be evaluated, and you will end up with values for n between 0 and 2n minus 2. Why 2n minus 2? Because those are all 2n minus 1 points. 2n minus 1 points. X of n is n length, h of n is n length. We know that the linear convolution, it's n1 plus n2 or n plus n minus 1. So you have 2n minus 1 points. And it starts from 0 to 2n minus 1 minus 1. So it's 2n minus 2. Okay, and we also have yl of n is equal to x of n convolve star with h of n. So this is our ordinary, the usual convolution that we learned before, and we did it mathematically, we did it graphically, and we did it also by using the tabular method. Now, we will define the circular convolution. Circular convolution. It has some differences. The first one is with the definition. So yc of n, so c sub c means circular, which is equal to the summation from k equals 0 up to n minus 1, x of k, h of n minus k modulo n. So you have here linear shift, you have here circular shift. This is why we call it linear convolution, we have circular convolution. Okay, the very important point here is that your y of n is only valid between 0 and n minus 1. So you have n-point convolution. N-points convolution. So you have n-points convolution. Okay, symbolically, we will call y sub c of n equals to x of n circle, and we will have n inside h of n. And it's also a commutative operation, so you can say that h of n circle n x of n. Okay? Okay. We would like to write this in a, some easy way. Let's see what can we do. If we expand those or this circular convolution for different values of or different indices of n, then we can say that, okay, yc of 0 is equal to summation x of k h of minus k modulo n. This is from k equals 0 up to n minus 1. So this is equals x of 0, h of 0, plus x of 1, h of n minus 1, plus x of 2, h of n minus 2. I already automatically did the h of minus 1 modulo n is equal to h of n minus 1. And minus 2 modulo n is h of n minus 2. Until we have x of n minus 1 times h of 1. Okay? Doing this for yc of 1 equals also summation from k equals 0 up to n minus 1 x of k h of 1 minus k modulo n, and this is equals to x of 0 h of 1 plus x of 1 h of 0 plus x of 2 h of n minus 2 and h of 1 x of 0, x of 2 h of n minus 1 plus x of n minus 1 h of 2. Okay, h of 2. So if we keep doing this, we will end up with some matrix form. So we'll have yc of 0, yc of 1, yc of 2, up to yc of n. So you have some matrix here multiplied by a column. Notice the column are the x's, x of 0, x of 1, x of 0, x of 1, x of 2, up to x of n minus 1. So this is x of 0, x of 1, x of 2, up to x of n minus 1. And you can figure out that this one here will be h of 0, h of 1, h of 2, up to h of n minus 1, and here h of n minus 1. Then this one goes down, h of 0, h of 1, up to h of n minus 2. And this one will goes up here, h of n minus 2, h of n minus 1, h of 0. And you will have at the end, at the very end, h of, we have here h of n minus 3, and we will the last element will be h of 1, h of 2, h of 3, and here h of 0. The one very last is h of n minus 1. So this is the matrix. Actually, this matrix is made only of one vector, which is h of 0 up to h of n minus 1. So the first column here is h of n. The second column, it's the same as h of n, but taking the last element here and take it and put it up here and goes down by the other elements. Then the next one will be going up, the next one will go up, and the last one is this one. This one is called circulant matrix. And circulant matrix is a matrix which is made by constructing one vector, taking the last element and going up, up. So it's like doing circulation of the elements. Okay, so you can perform the convolution or the circular convolution of two vectors by forming the circulant matrix of one of them multiplied by the other one and get the answer. But this is not you can do this by computer, it's easier. Let's see how we are going to do this. If we take an example, if we let x of n equals to 1 to 0 and 1, and let's take h of n equals to 2, 2, 1, and 1. And we would like to find the circular convolution of those two vectors. So what we need to do here, or find yc of n, which is equal to x of n circle 4 h of n. Okay, so this is what we are looking for. So to solve this, let's do the yc of n equals to summation from k equals 0 to 3 x of k h of n minus k modulo 4. So yc of 0 equals to summation x of k h of minus k modulo 4 from k equals 0 up to 3, and start substituting values. It's x of 0 times h of 0 plus x of 1 times h of 3 plus x of 2 h of 2 plus x of 3 h of 1. So this is equals to 1 times 1 plus 2 times 1 plus 0 times 1 plus 1 times 2, and it's equals to 6. So YC of 0 is equal to 6. YC of 1 is equal also to the summation from k equals 0 to 3 x of k h of 1 minus k modulo 4, and this is equals to x of 0 times h of 1 plus x of 1 times h of 0 plus x of 2 times h of 3 plus x of 3 times h of 2. And it's equals to 1 times 2 plus 2 times 2 plus 0 times 1 plus 1 times 1, and this is equals to 7. So this is equals to 7. Foot. Okay. YC of 2 is equal to summation from k equals 0 to 3 x of k h of 2 minus k modulo 4, and this is also equals to x of 0 times h of 2 plus x of 1 times h of 1 plus x of 2 times h of 0, and the last one is x of 3 times h of 3. And by multiplication, 1 by 1 plus 2 times 2 plus 0 times 2 plus 1 times 1, and this is also again equals to 6. And the last one, YC of 3, which is the last one in our convolution, because the convolution has only n points, 0, 1, 2, 3, 4 points, and this is the summation from k equals 0 to 3 x of k times h of 3 minus k modulo 4, and by expanding the summation, it's x of 0 times h of 3 plus x of 1 times h of 2 plus x of 2 times x, or h, sorry, of 1, and x of 3 times h of 0. If you apply those, 1 times 1 plus 2 times 1 plus 0 times 2, and the last one is 1 times 2, so you have 5, 2 plus 2, 4 plus 1, 5. So our YC of n is equal to 6, 7, 6, and 5. And it's here. So what I will, you see that this is a tedious job, doing all the mathematical things. You can do it also by graphically, but the easiest way to do it is by the tabular method. So we'll see how we do it with tabular method. Okay, to do the tabular method for circular convolution, I will do the same as we did before. You have the table, you have n here, 0, 1, 2, 3, but because you have only n equals 4 at this case, so you have here 4 modulo 4, 5 modulo 4, and 6 modulo 4. Okay, our x of n was equal 1, 2, 0, and 1, and our h of n is equal 2, 2, 1, and 1. And we will start multiplication. We'll do the same thing as we did in the previous tabular method for linear convolution. We'll do the same, exactly the same, but we will end it with some extra steps that we have to do. So 2 times 1 is 2, 2 times 2 is 4, 0, 2 times 1 is 2. So we take a space here, we go to the next one, 2, 4, 0, and 2. The third one is 1, 2, 0, and 1. And the last one, 1 times 1, so 1, 2, 0, and the last one is 1. Okay? Now, before we notice that this is the linear convolution, and you end up with those values. If you do the linear convolution, it's 2n plus 2n minus 1 points. So 4 plus 4, 8, minus 1, 7. So you have 1, 2, 3, 4, 5, 6, 7. So you have 7 points. In the circular convolution, we need to find, it's only for defined from 0 to n minus 1. So we look at those here, those indices is 4 modulo 4, so it's actually a 0 index. So those 3 elements should move and be here replaced by the 3 elements. So we're gonna take this one here, 2, 0, and 2, and we will cancel this one. For those 2 also, we will move them to the 2 elements here. So this one will be 1, and this one will be 0, and we will cancel this one. And the last one here, it's 6 modulo 4, it's equal to 2 actually, the index 2, so you have only 1 element here, and so we will cancel this one. Now so this is the length of your sequence from 0, 1, 2, 3, 4 elements. If you add those, 2 plus 2 plus 2 is 6, 7, 6, 5, which is the same as our, so YC of n is equal to 6, 7, 6, and 5. Okay, so this is an easy way to do the circular convolution. You do the linear convolution exactly the same, but instead of those empty spaces, you take whatever extra here, 4 modulo 4, 5 modulo 4, 6 modulo 4, and 4 modulo 4 is 0, so you take it, the 3 elements, you take them here, the 2 elements, 5 modulo 4 is 1, so it's index 1, you put those 2 elements in here, so you fill up the table, add it, and you have the circular convolution, okay? With this, we end up this lecture talking about circular shift and circular convolution, and we will continue next time with properties of the DFT, because as I mentioned at the beginning of this lecture, we needed this lecture so that we can study very well the DFT properties in time domain and in frequency domain. Thank you very much, and we'll see you in next lecture. Bye-bye.